Okay, so this is one of my favorite chapters because work and energy are really kind of fun to deal with, and the calculations often make more intuitive sense for me. And as you're kind of advancing through these problems, there are certain learning objectives. First of all, kinetic energy of rigid body first, and then the idea that couple moments can cause or responsible for work. And then principle of work and energy and conservation of energy. For kinetic energy, we can take an element and sort of say, okay, look, there's an element, some arbitrary distance r from, say, a center of mass, and x bar, y bar correspond to the distances r in the x and y directions, respectively. With z, I'm not going to worry too much. This is still a two-dimensional world. And if I do that, I can say, well, velocity at the center of mass, I can say that the velocity at the center of mass is v sub g, and each of the elements might have different velocities, so v sub I. And so if I say, look, Ti, which is the energy of the kinetic energy, of element I, it's 1/2 a vi squared dm. T, then I can integrate over the entire body, the entire mass, and I get 1/2 m vi squared dm. T, by the way, comes from the French word travail, which kind of fun to find out that that's what it is. Vi is equal to Vg plus Vi with respect to g. So it's again a relative velocity problem in the sense that I need to know where everything is there. And I can say Vi is equal to Vgxi plus Vgy. So I'm just doing that. Okay, so that makes sense. And then I have a rotational component, which is omega k crossed with xi yj over there. So I've got all the terms there, and I end up with this expression, which is Vi equals Vgx minus omega y, the distance to the element, plus Vgy plus omega x in j. And again, distance to the element. So if I take the dot product of that, I end up with this mess, and this mess is a whole bunch of terms, Vgx squared, Vgy squared, and then these other omega squared terms, omega squared y squared, omega squared x squared. Then I have two other terms in between. Those two terms are about the center mass because that's the way I've defined everything here. And those are kind of interesting because I can get rid of them. And I can get rid of them because I know that if I do an integral all the way around the object, that half of it will be in the plus y bar and half in the negative y bar, and the same for x, half in the positive x bar and half in the negative y bar. So I do the integral, calculate everything, and these integrate about the center of mass. And then I'm stuck with these terms. But that last term is Ig, and the first term is the expression I already had for translational kinetic energy. So I have translational kinetic energy and a rotational kinetic energy that have appeared because of the rigid body expressions. So here, right, these two expressions. So if I know I have rotational and kinetic energies in these problems, that adds a bit more to think about as I look at these problems in terms of everything. So in terms of the second law, I go back, motion is parallel, again, this is translational motion, T is equal to 1/2 mvg squared. In the case of rotation, I have 1/2 mvg squared plus 1/2 ig omega squared, and I have 1/2 ig mrg squared omega squared. And that last term over here, because this is rotation, is also interesting because that's my parallel axis theorem. And that was something we've emphasized in the lectures, in the course, and everything, and in the homework probably, throughout the course. So T is equal to 1/2 I naught omega squared. So I can get rid of that translational component if I switch to the pinpoint. General plane motion, not much I can do. I've got to combine both terms, and I have rotational and translational kinetic energy. These are force, velocity, and distance problems. And so in terms of the derivation and what you've had before, you already know sum of forces is equal to mass times acceleration. But in this part of the course, it is mv dv dx. And so there's your distance, there's your velocity, and there's your force. And we'll be looking at a lot of problems, and you really need to be able to identify it, and I strongly, strongly encourage you to look at old final exams to try and pull some of this material out. But you do have to have some sort of translational or rotational displacement in order for things to happen. So you'll either have a theta or an x, y, z. So forces that do no work, work of a couple moment, because they displace both in the same direction, and also forces that are normal. So you have here, for example, a force that is going directly in towards the center, and it never displaces, and force at the pin never displaces. With rolling at the center of mass, it displaces in the horizontal direction, and we already know that displacement in the horizontal direction doesn't count towards work. And then for a work of a couple moment, we also have nothing because it displaces a negative amount in one direction and a positive amount in the other. In terms of conservation of energy, still the same conservation of energy equation, T is equal, or T plus work done is equal to T2. But I'm going to combine a number of things here, spring, gravity, conservative forces, with non-conservative forces like moments and frictions. So I have T1 plus V1 plus U1 work done plus T2 plus V2. So that's kind of, here I'm going to deal with conservative forces, and here I'll deal with the non-conservative forces. So conservative forces are always going to be, in this course, spring, elastic, or gravitational. So we can deal with those there. In terms of conclusions, energy and work have been defined. Conservative work forces allow potential energy, and we'll talk again.